in the walkthrough, and you must start practicing them. And we will then continue in the next module of our discussion in terms of the lambda calculus. We will start on discussing on the typed lambda calculus after Srijani finishes on the language discussions. Okay, so it is over to Srijani now. Please take over, Srijani, and
Yeah,
start
yeah, please,
discussing on the
please
language.
focus. Yes. Sir, I think my screen is visible. Show me.
Yes, it is.
Yes, okay. So earlier, just to recapitulate what we actually discussed on Monday, so we were discussing on the basics of functional programming languages and constructs which are used commonly, and how Haskell is a purely functional language. So we had discussed about types and classes, and we saw how to run a Haskell program, the various other predicates, the data structures, and obviously we had an example of how to define a function and everything. So we'll continue from that point, and we'll talk about some very interesting facts on Haskell, and then we'll move on to Scheme and Lisp. So Scheme is we are going to not talk much on Scheme, some examples, and Lisp again. So but then once you understand Haskell, Scheme and Lisp, I'll be showing out only those points where you'll be seeing the differences with Haskell along with the common predicates and functions and everything. Okay, so let us get started. Okay, so I had wanted to discuss some more on functions basically, where Haskell has this guards condition. So guards are mostly equivalent to normal if-else blocks which you use in C. Okay, so if they're like for example the BMI, if you just want to calculate the BMI, just BMI of your body and everything. So in that case, what you see here is the type. See, whenever you're defining a function, as I had mentioned before, Haskell is statically typed. So if you define a function, you have to mandatorily define the type of the function. By type, what we mean is that what is the input and what is the output. So and the type of all the inputs and type of the output. Or if there are multiple outputs, then obviously multiple outputs. Okay. So if you see BMI tell here, weight and height, so they are just doing some calculations, and if it is less than some numbers, then this is what comes up. Okay, this is the string which is your output. Okay, so it takes in three real values, compares it, and then two real values and compares it with a real value, and then it gives you the type string. Okay, or else there is a catchphrase, basically like a default switch kind of thing. Like obviously, yes, if you just relate it with the essence of C, it's going to be easier. Then a normal message comes up. Now, what we see here is that in terms of space complexity and time complexity, are you seeing something here? Because you see the calculation weight by height, square, weight by height square, what you see here is done thrice, which is not required. Okay, so this is where, in Haskell itself, in the functions, you can actually have a where clause where you can actually define this as a variable which is applicable only for that function. Okay. So you're not using any let binding here, that's why. So that is where I'm just showing you the way of writing different types of functions. This is just the way of writing it and the way of understanding it. So basically, so you can just, have a variable defined and that can be again used. Now, these are the guards condition which are regularly used in Haskell. You can use them while you are coding. Now, max. Okay, so we are trying to find out the max of two numbers. Okay, so this function again here takes up two numbers and provides a number, whichever is max. So have a look at how the function is defined. Okay, so and okay, one more thing here. There are two things to notice here. If you can notice, I have a max apostrophe. Why max apostrophe? Because Haskell has a max inbuilt function. So then that will actually not allow me to compile. Okay, I cannot have it's same thing as any other programming languages. We cannot compile with the same inbuilt function name, which is already there. And order is a type class. Okay, earlier we had discussed about type class. Order is a type class which signifies that it is going to do some kind of comparison. Okay, because we are comparing these two, where integer a, I mean, I've just mentioned here a, basically. So so that is being represented by the order type class. Now, if you see, if a is greater than b, then a, otherwise b. It's a simple function using guards condition, but this is what we are defining apart from the max function in Haskell. Okay. Now, so this is just to understand the different type of functions and how you can define that in Haskell. Now we can also have recursion. Okay. Now here are the two. If you see here, I mean, this is the first version of maximum. We are finding out the maximum of a number in a maximum number in a list. Okay, that is why the type of A is within brackets. It signifies a list. So this can be done. This is done in two ways. One is in the second definition. I have actually used max, which I have defined. You can use this max also. You can use the inbuilt max also. And here the whole thing has been again defined. Like if it is greater than this or this. So the whole list is taken as an input, and then the same thing follows. Okay, but one thing you have to understand is that you have to have the the base, the edge conditions have to be defined. Like if it is an empty list, what you do. If there's a one element in the list, then what do you do? So all these things need to be mentioned whenever you are defining a function, or else it will give you unprecedented errors on encountering those kind of inputs. Okay, so just have a look at this. I have written two types of recursion here, which actually one with using another inbuilt function, or you can use your own function, and where you have done the whole thing yourself, and you're having the recursive call here, basically the same essence, where you are just repeating it based on this recursive call here, maximum. So you have non-recursive and recursive varieties for every function. So, but recursion is possible in Haskell, and that is what I'm trying to show here. Now, I want you to tell me, what is func1 doing? I mean, I really want anyone of you to understand this function and tell me, like, just give me, like, you just tell me, like, func1, it's taking in two inputs, okay? So if it is taking in two inputs and it's giving you a list. So just give me any example of those two inputs and just tell me what list will be created using this function. Num and order are type classes. So I mean, I'll just give some time, maybe 30 seconds or 1 minute, just to, it would be good if you just have a look at this function. No, it's not factorial, Nagesh Patle or Dong, Sri Vivek. Just have a close look. I'll again upload this. Because I'm using my Linux machine, that's an issue. Just a second. I think someone gave the right answer. Just a second, I just moved off and yes, Shomnath, I think yes. Can you give an example, Shomnath? Like you said n times x in list. Just give an example. Like there are two inputs, and what would be the list be? What the list would be created? I think Pankaj, that's you coming to the right direction. Just give me an example. Okay, fine. So I'll just get back to it. But anyways, you both are correct. Devojyoti has given an example. Yes, 2, 3 would give 3, 3. No, I think it will give you 2, 2 in that case. 3, 4. No, yes. 3. Correct. Yes, absolutely correct. So yes, so this is what the function is doing. So I think you have understood the definition of the function. Is my screen visible? Showman, this Sublime is visible, right? Yeah.
Mm-hmm.
Okay, thank you. So thank you, Devojyoti. All of you who have replied, the correct answer is that. So this is what you have to understand, and you have actually understood the syntax of Haskell. Then it's good. Now we'll get on to current functions, basically. Now, okay, so for curried functions, you have to understand the order of evaluation. Okay, so I think currying has already been taught by Sir. It's just few examples I've given here, like max 4, 5. How do you actually the order? You just take up the first argument, evaluate it, and again then take up. It's just an example. So I'm not getting into the concept. So just how it is used in Haskell. So that part is there. And now we come up to some of the predicates and functions which are used in Haskell and which actually will help you to operate on Lambda functions also. Okay, like maps and filters. Okay, so if you take a list here, so the definition of map, the Haskell function, a function for map has been, I have provided that here, how you define map. Okay, just for your reference. Now, if I use map, for example, like +3 or whatever I like replicate 3 or something over a list. Okay, so this is what it comes up. So if you see like +3, it applies this to all the elements of that +3 is applied to all elements of the list. So that is what map does. So you take any function there and you apply it to all the elements of the list, basically. Okay, like see if you see replicate 3 here, 3 to 6. So it is replicating all elements of the list 3 times and it is creating a sublist within lists. Okay, and then you have filter is something where you are actually extracting some portions or based on the values of the elements of the list. Like if you are filtering greater than 3 valued elements from a list, it is going to give you that. Okay, similarly equals to 3 and so map and filters are very important and there's also another which I had told you earlier was take. Okay, so take, map, filter, these are very important operators which you can use on the whole list, basically. Okay, and you can also have infinite lists. So I'll come to infinite lists, and based on infinite list also you can use them, so there's not an issue. Now lambdas. Okay, so lambdas have been taught by Sir, and so it's just that we need to understand how do we write that here in Haskell. So what you see is lambda is nothing but the anonymous functions here. Okay, you are like, for example, map plus 3, you can actually add here you can add a function here which you don't want to name, is just applicable only for that part. So you can write it a lambda for it. Okay, so I'll just show you here. So you see here, if you are writing, see, I'm writing here map +3. So you just can have a lambda /x. That is how you write a lambda in Haskell. /x gives you x +3. So that is what takes up an element of the list and adds 3 to it. So these are functions. And so this can be added here instead of the map. Okay, so any anonymous function, any small requirements or larger, smaller, that doesn't matter for that. Any requirements which is applicable for that context, you can just have an anonymous function built in, which will be doing the same action as any other operator functions there, which are available with Haskell. Okay. So here, if you see zip width here, we are adding how to do the zip width. We are adding a lambda here, which is an argument to zip width, and the list here on which the lambda will work. Okay, so this whole calculation is being applied to all of these, two lists here. So you just have a look at it. So it's the same thing. If you see here, when I'm actually, and this is how you define a function add3 using lambda. Okay, I think it's clear till now. Before going to input output, I would like to know if there are any questions. I don't think so. Okay. Okay. Now let's get into input and output. Okay. Now this is just some input and output, the put strlen and the get strlen. All these are normal printf and scanf equivalents which are available in Haskell to take inputs from users and give them output. So basically get line and all these things. So these you just can go over through it, like I've given you some example here. Okay, so here, like, you can have a put a strlen to get your name and get line to get whatever is there, and then you can have again a print one, again a put one. So these are few of the things which you use when you are actually coding in Haskell. So not very important in understanding Haskell, but just for your information that these are the operators available. Okay. Now we come to the lazy evaluation strategy advantages which we have in Haskell. Okay, so here I'm going to show you a very small example where you have to understand what is being done. So in Haskell, if you are adding two numbers, for example, so this is the definition of add xy in Haskell. It is adding the first number only. Okay, just go through this example. I'll explain why I'm showing you this. So add xy will give you x plus x. Okay. And in Python, how do you define it? You define an add function and you return x plus x. So in both the cases, y is not used in the function's body. It can happen, obviously. You can have a function which is not dependent on the arguments. Okay. Uh, Maybe later it will be taken in and everything. Now, if I want to do add 4, 5 in Haskell, so what would it give me? 8. Okay, and if I want to add 10, 89 slash 89 divided by 0, which is again, it's a, you can, that's going to, so, but in, the result is 20 in Haskell. Okay. Now, interestingly, can anyone tell me, obviously in Python, you will get an error for the second call. Why? Because this 89 divided by 0 will be evaluated and it will throw an error. So it will evaluate all the arguments, whichever are present for the function, and then it's going to do the operation x plus x. So, but Haskell does not do that. Why? Because Haskell follows lazy evaluation strategies. If it is x plus x, it will just, pick in x, see if it is a valid number, do a plus x, and give the result back. So this is what comes up in Python, a division by 0 error, which is most expected. So they've taken this from the Python screen. So if you go back and you run this, that is what you get. Okay. So this is, I'm just showing this example. Why? Because I want to show you what actually is meant by here in lazy evaluation, basically how you actually can get an error if you don't have a lazy evaluation strategy followed in the language. Okay. Now, so what happens is that, so this is where I want to discuss on the infinite lists, basically. So in Haskell, you can have infinite lists. Okay, why is it important? Like, I think if you have bigger functions, basically, like something like this. So if you just take 5 elements of that list or 6 elements of the list, it will not iterate throughout the list and then give you 5 and 6. Just take the 5 elements and give it to you. Okay, so if you're finding out like Armstrong numbers or something, or which, like, so you can just take the first 100 of that list and find the Armstrong numbers from there. You have all those opportunities here. So if you see the Armstrong numbers, I've defined Armstrong numbers here. What I'm doing is that I'm just filtering the first 100 Armstrong number and just taking the first 10 out of it. So, I mean, within 100, there are only 4 Armstrong numbers. So there is no point in actually, so I can just take 4, filter is Armstrong 100, or maybe even make it 50. So I'll just get maybe 2, basically. Okay, so this is how your computations are reduced if you use an infinite list. Even if you don't have to worry about the length, you can just operate on infinite list. So you can just try this out with Armstrong numbers. So you can just go back and try this out. So this is a very beautiful way of actually where you can just use the take and filter operators and work on the first 100 numbers you do. And then if you want the next 100, just increase that. So it is that flexible. Okay. That is the reason due to this why your infinite lists are supported is due to the lazy evaluation strategies in Haskell. Okay. So I'll show you the one that I had shown a example there and worked out. That example has been worked out. So now I'll show you that lazy and eager evaluation. So going by, so if you see this here, so lazy evaluation in Haskell here, how do you actually do a lazy evaluation? So you have, it's a square function which it takes in square 2. Okay, so if you see, one at a time the arguments are evaluated, like all of them are not like arguments are not evaluated till needed, sorry, arguments are not evaluated till needed. So if you see square 2 into square 2, okay, it's actually expanding, and then 2 into 2, and it's not evaluating any one of them. When it's at the end it will evaluate 4 into 4, and at the end 256. But if it would have been eager evaluation, this 2 into 2 would have been earlier evaluated 4, and then again into square 2. So if you see the end result of any sub expression are being evaluated at the first and then carried on, and then you get the results. Okay, so that is where the lazy evaluation strategy in Haskell works. So I think for Haskell, if there are any questions, because this was a time noted for Haskell basically, and we have looked into various, just to recapitulate what we have done with Haskell, like the various ways of running a program, the functions, the data structures, the predicates, the list operators, and lambdas, recursion, currying, and we have talked about input output operators, as well as we have talked about some static, how statically type, because I showed you a case statement where the output had to be of the same type, and then we saw about the type inferences, and we saw about the lazy evaluation strategies in Haskell and infinite lists, and how you can work with infinite lists basically. So we'll end up on Haskell now, and we'll get into scheme. Okay, so I'll be sharing all these things, like these are various other I mean, programs which can be written, and you can just have a main function to define it. The one which I showed the earlier time. So I'll close on Haskell. I'll see if you have any
Ma'am, excuse
questions.
me, ma'am.
Yes.
Ma'am, in Haskell, it is necessary to do function declaration. Like we have to assign data types. What will be the data type of the input and what will be the return type in the function? Or
Yes, yes. Yes, you have
it
to.
is necessary, or we
Yes,
can.
it is necessary.
Okay.
Okay.
Yeah.
You have to define type, basically.
Okay.
You can try that out without that, but it will not work. You can just try out Haskell. I mean, can I know who's speaking? I can get back to you. I mean, you can get back to me after trying it out.
Okay. Aryaman.
Oh, okay, okay. Because see, that is what the static inference, static typing issues comes up for Haskell. Okay,
Okay.
so you have to define the type. But what you need to understand is the type classes. There are various type classes in Haskell, order and num and float and read and all these things. They specify different types of, types. Basically, like order is for comparison, num is for numbers, and real float. So you mention that you can have a type class mentioned, or you can just write it as integer, float, or whatever. I mean, okay.
Okay.
So here, I think you have seen this example, and you are asking me. Just a second. So you see, whatever I've defined here, I'm actually having, see, all the types are being defined here. Can you see that?
I,
Yeah. Okay. So these are functions which I'm running in this terminal, as I showed you that day. Okay. Now I'll go to Lisp then, Lisp and scheme. So I'll start with scheme. So we'll finish scheme fast, because scheme is like, there are few only, and it's not very widely used like Haskell and Lisp. So is my screen visible? Showman.
Yes.
Okay, yeah. So scheme it differs from Haskell primarily in the area of being dynamically typed. Okay, and apart from that, obviously it has other operators and prefixes and everything. So we'll have a look at this. So first is it's like prefix notation. All the expressions are evaluated, arithmetic expressions. Very simple, not going through it. Okay. So like quotient and everything, and all obviously these are again predicates. Now the basic data structure types are in layer scheme is also lists. Okay, and it has various operators on it. Like you have car and CDR and cons, length, reverse, append. All of these are very highly used in defining any functions of list, any functions of scheme basically, which are based on lists basically. So car will give you the first element, okay, and if you see, if you have a multiple list here, so then this comes. So you can just have a look at it. These are like very simple things, and CDR will give you the whole list without the first item, okay, without the first item, and then you have the length and reverse. So these are inbuilt predicates or list operators which comes up. Okay. So if you see here, so what is quote doing? Quote is actually creating a list out of it. Like this is constructing a list basically. Huh? So plus 3, 4. So it's the same as this. So you can actually quote the string construction. I'll come to construction after this. Okay. So quote and quote cons, I leave it up to you to decide what is it, how would it come up basically, quote cons, and again a quote on it. Okay, let's not like practice it out. We'll not discuss that in the class. Okay, now the dynamically typed nature, which I was talking about, is like if you see here, like if you 3 is greater than 2, I can have two different types of outputs. ES is a string, 3 is a number that is allowed in scheme, which is not allowed in Haskell. The major difference points with scheme and Haskell. Okay, so and then you have other operators again, like case and cond, like whatever you want, like if it's 3 is greater than 2, all these things will be returned equal. Just simple examples, I'm just going through it just you can have a flavor of scheme basically. How installation instructions are given here. Just a second, all the installation instructions are given here. Not Yes, so this is the installation instructions here. You need, this is for Linux. You need to just do a sudo apt and then type MIT scheme. Again, you'll get a interpreter like GHCI in Haskell. So that's the same thing you'll get for scheme. Basically, all the installation instructions are given here. So now after this, we will come to, so you have case, car, CD, and then you can have a lot of functions you can write using case and cond and car and CDR. So all these operators mostly which can come handy, and then you have the and or expressions which are going to give you true or false. Okay, so basically the Boolean operators. So the logical operators and the Boolean operators, everything returns the true and false here. And then you have a let expression. Now this is where I wanted to come to, like I think I want you guys to have a look at it first and explain. Maybe someone can explain also, because it's already there, so there's no point in moving it. So the let binding is here also, like Haskell, and you have inner scope and outer scope. Okay, so let me first have a look at this function here. Okay, the one which I've highlighted. So it is taking in two lists, 1 and 2, which has elements A, B, C and D, E, F, and is doing a operation on it using cons and car. So this is the output, A dot D and then B dot. So you have to understand the parenthesis very well in scheme. Okay, so can like anyone I mean, is anyone having any issue to understand it? So if I just go through it, so it's taking the first elements of both the lists, car list 1 and car list 2, so A and D, and it's doing a construction. Okay, so then a list gets created with a parenthesis, and then on top of that it is again doing a construction of CDR list 1 and CDR list 1, taking the car of that. Okay, so B dot E. Okay, so this is how this works. I'm just going a bit slow here. So this is how it works. The construction and everything. Now nested let expressions again, if you see, the A value here is 4. And then again A squared, you are giving another value. So it can have the same name as you see in the next expression where X is assigned a value 1 here. And then again X is assigned a value of X plus 1 here inside the inner scope. And then again there's an X plus X, and then it comes up to the outer scope here. Okay. So this value X1 is getting kind of here, and then that is being added here, and then within the inner scope only there's an X plus X. So you're getting a 2 here and 2 plus 2, 4. So within the inner scope, it gives you a value of 4. The outer scope value is not applicable then, same as scoping in any programming languages, just showing you how it can be done here and how it is applicable here. To define a function, you use the keyword define here. Okay. For Haskell, what you were using. If you remember, I'll just open up the Haskell sheet. Yes, so for Haskell, for defining the functions, you are just using this, the function name and the xy. So I'll go to a proper function, maybe that way it would be easier for you to, yes, so like BIM tells, just define it. But here you have to use the define keywords and then whatever you want to define. And a lambdas here, obviously you can have anonymous functions here. So use a lambda keyword. Instead of a slash x as you used in Haskell, this is a lambda x basically. So this is just the point where I'm showing you how it is different, how the constructs are also different for Haskell and scheme. Okay, so I'm defining a square here, and this is how you define a factorial in scheme. So I'll just give you 30 seconds to have a look at it, basically how you're defining it. And you're defining this function using a lambda here. Okay, so this is the factorial definition, which is a anonymous function body which is attached to the name fac. Okay, so have a look, it's the same thing. So it uses if, it gives you the edge conditions, and then it's a normal, and yes, it also uses recursion. Okay, so it also uses recursion along with lambda. So this example has all the 3 variants. That is why the reason I had given this to you. So have a look at it while preparing for the scheme language. Input output again, just to give you what type of input output operators are available with the languages, read and display. So just remember that there was like put strl and get line. Okay. And you have the list operators here also, a lot many list operators here if you see here. Okay, so you have apply max, you can add map odd, various other list operators which can be added here in scheme basically. So what we see is that people code more with Lisp and Haskell. Why Haskell? Because mostly it has a lot of features. With Scheme, basically, if you want a functional type language with only dynamic typing, you can go for Scheme. For Lisp, why people use Lisp is that I'll show you clearly because of the, the imperative, partial imperative structure of the Lisp language and how you can actually write loops and link elements, and so those part I'll come to. So this is all about scheme. Scheme actually we used to like, it's about have some examples which this could be worked out and everything. So working out, and it's a bit tedious as a language. You have to understand the parenthesis well. Parenthesis is very important in scheme. So one parenthesis is wrong, and so the whole thing goes wrong. Okay. So have a look at this. I'll be sharing these worksheets of scheme. So mostly the important part is that I will come to Lisp, where I'll show you the differences, major differences between languages which are purely functional and languages which have a functional as well as imperative flavor. Okay, so just open the Lisp and let's get started with Lisp. Before that, I'll ask if anyone has any questions on scheme. Yes, indentation is necessary, Devojyoti. Otherwise, it will not run. So when you actually use SBCL and the MIT scheme when you type, and if you don't indent, there's an issue. So once you start running, because in the interpreter itself, that will be an issue. And the errors in scheme are not very self-expressive at all. Okay, you can have a try, not very self-expressive. So it's very difficult to debug in scheme. It's from the personal experiences I'm sharing, because it's mostly errors are related to either parenthesis or indentation, basically. Okay, so I'll get moving to Lisp. Okay, so these are the installation instructions for for Lisp. Simple installation instructions. Install and just check. Okay, and it would be great if you also could come back with some more observations, maybe which I've missed, and we can have a discussion on that. Okay, so these are all the programs which are written here are all run on the interpreters and then copied here. Okay, with the proper way, the way it was run, everything has been copied. So you can have a try at that. Okay, so again, very simple things at first, like you can have the, arithmetic operations and how it is evaluated and everything. So again, it allows mutable variables. It's not purely functional, and obviously it follows lazy evaluation. Okay. Now, and I think it's dynamically typed. Lisp is also dynamically typed. Now, Clisp is the compiler which you can use to actually compile programs of Lisp. So similarly, like GHC compiler of Haskell. Okay, so that way it is much more easier to write huge programs as you can do in Haskell. You can do that in the Lisp also. And then we have the various other, data structures here. So these are the lists again, okay, where you can have all these predicates which are available in even in scheme. So you see these predicates are same as, in Lisp basically. Now, functions and lambda. So we'll come to the main important points now. Functions and lambda. So you use a defund keyword and you give the name, the parameter list, and optional documentation string. So defund average now, and this is how you write that basically. Okay. Area circle. So because you see there are no types here where you have to define types, so it's dynamically typed. So you don't have to worry about types basically. Okay. So this is how you write Lisp functions. Okay. And you can also have optional parameters in Lisp. I'm just showing you the features which are distinct in Lisp, not available in other languages which we discussed. Okay, so you can have optional parameters, and these are the outputs. So if you have a show members functions defined here, then you can actually, so if you run these, terpre is just a new line. Okay, terpre is a new line, just so you can have this, output here provided. Okay. Now, rest parameters, rest values, so various other functions which, various other features which you can do with Lisp. Try out one of them, like optional and rest parameters, and all these have been provided here, the values. And this is how you write lambda here again. You use the keyword lambda, and then you can have any kind of functions defined. Okay, so if you actually run this, you'll get a value of 51. So it's just based on the normal lambdas which is done here. Okay, and this is the input list 4293. It's not a list, it's input numbers basically. And then you have map functions again. Map functions are there then, as you see, in all the three languages. Very important: map, filter, all these functions are actually list operators which are used here. Okay. Map car. And interestingly, Lisp gives you a lot many predicate functions. Okay, so these are all the predicates which can be used. atom and equal and all these things. So this is what is your output here. The outputs are provided here. Either it is true or false or nil. Okay. So all these predicates are provided here. Mostly they give you Boolean results. Now if you, I've also defined a factorial here for you using the recursion, obviously. Okay. So I'm using a predicate here, 0p. Okay. So this is if you see this is how it is defined in Lisp, and this is how it is defined in Scheme. Just to show you the syntactical difference. So if you see the essence of functional languages mostly are same. It's just the syntaxes are different and the predicates are different. Okay. And obviously the way of writing, the style, the parentheses and indentation, those will be different, but essence remains the same. Okay. And obviously you have you can do operations on strings, various operations like equal, greater. But these are all the operator values which I'm showing you that okay, these are the values which you can do, and so just have a look, like you can compare, and all the outputs are provided here. Input output, again you have to know what can be done. So you have a print here, I mean PRINC. Okay, so you have that, and then you obviously have a set Q which actually works like your scanf. Okay, so now I'll come to some Lisp programs which I've written just for you to understand about loops and everything. Okay, so here is one program where actually I'm building an array. Okay, so and I'm setting the values of those array. Okay, so this is where I refer the array position. Okay, similar to you can think of this as the address or references basically. So I make an array of size 10 and I refer those positions and I add in the value like 25, 23, whatever it is. Okay, so initial contents also I can specify the initial list here based on which the array will be done. So you can run this. You can run this. I'll share all these codes. So where you can actually what you are trying to do here is that you're trying to you're not mutating the variables here, but you can do that in Lisp basically. I'm just showing you how to make a composite data structure in Lisp basically using this. Now there's another interesting example which I want you to solve and tell me what will you get in if you are doing print array aij. Can anyone, I want to all of you to solve this Lisp program here. I showed you the syntaxes. And it is using loops, if you see, do times. Okay, so I'll just give you some time. Just tell me what would be the output of this. And the X here actually, it is just a string which is getting displayed. Huh? Don't be bothered by that. So a string will be the number I, that X, and then J. So if anyone could come up with the answer. I'm actually building the list using an operation. I'm building the array values for the array locations using a operator here. Devashi, it has prints all elements of the array, but what does it print? Yeah, it's a 2D array, but what does it print? The values are also mentioned. Yeah. Okay, yes. Okay, so Devashi has come up with the correct answer. I'll show you the output of this, but Okay, so I think the output here for this is here. So this is what it's going to print. So the element value is based on the values of I and j. And it is doing a multiplication here. And this will also be printed because you're actually printing array here, and the list prints this as a string, and then this is the whole thing which is getting printed. Even the value applied there is only this rightmost column, but just for the output sake, you have to understand what the program is doing. Okay. Some more on Lisp programs. Basically, you can have any kind of delete if and everything, and then you can have a write x, so you can get it from the users, and so all these multiple such programs have been defined here. Okay, sort and merge and vectors and lists, which you can have a look. So using setq and prink and everything. Okay. I'm sorry, that will be actually a typo mistake, was that will be PRNT. So anyways, so these are all our runnable programs which you can run using the CLISP compiler and get the output, and also work on it. So okay, I will be proceeding to the last part of the comparison which will make between Lisp and Haskell. So I'll just see if there are any questions. Okay, so this will take the next 5 minutes on Lisp and Haskell. So what are we doing here? Like, how is Lisp and Haskell different? So if you see this here, okay, so this is the predicate. So that Lisp is mostly based on predicates and a verbose kind of syntaxes, which are mostly there for, it is not functionally bound, basically, the way it is doing it for Haskell. Now, if I want to just take all the elements from the list except the first three that satisfy predicate P, so what I do in Haskell, so I used a take 5 and I then filter P. P I have already, filter, and then I do a drop 3. Okay. So here I can just do it using, so this is what you're seeing here is that all the operations of Haskell is defined as terms of functions which are piped. It's similar to Linux pipes, if you can remember here. It's same thing. But if it would have been done using Lisp again, so you have to do this. So start 3 can be just starting at the third position, just do a drop 3. So if you see, the syntaxes has a mix of imperative as well as purely functional language features. Okay, so this is how you mentioned it. So I'm defining 3 functions here: take, filter, and drop, and I'll just do a normal dot of this. I mean, just piping it basically, same as Unix. Okay, and if I want to do anything, like if you don't want to satisfy the predicate, just use a not. But again, in common Lisp composition, it would be this again. So this is just a comparison of how you write functions, or how you write not a function, I mean how you write whatever you want to write, algorithm using Lisp and using Haskell, basically. And if you want a looping, basically, what it is doing here, it's like, interestingly, when you loop in, this is how you loop in using a loop macro, you do that in Lisp, but this is what you do using a Texas range, a take, and a filter predicate in Haskell in 2 separate functions. It's going to give you the same result, 2.4 and 2.4. So just I mean, this gives you that how these two languages are different and how you can actually, mutate variables. Obviously you cannot do that in Haskell. Everything is within functions. You have to compose functions on it, and the output of one function goes as an input of other functions. That's fine, but you cannot mutate variables. But you can do that using, obviously you can do that using Lisp. That's the reason you get this imperative flavor. And the rest you saw all. So just summing up for Lisp, basically. So again, based on your functions and lambdas, what you can use, and various parameter types which you can have in Lisp, how you can actually define arrays and loop over it. All these programs are given here. And input output again, and some basic comparison details of Lisp and Haskell. So these are the three languages which you actually have looked into: the syntaxes, the way it is works, the evaluation strategies, the typing strategies, and also whether how a pure and a not pure language looks like. The not pure language is Lisp basically, and a pure language is a Haskell and Scheme. So I'll just check if there are any questions. Okay. So I'll just end here then. No questions on that. I'll be uploading the worksheets and everything. So I hope this was understandable. Sir?
Thank you, Srijani. Thanks for the walkthrough with the three very important functional programming languages, and the reasons they are very useful is the fact that in several domains we are trying to use functional programming now because of some of the aspects of software engineering which are very difficult to ensure from the usual programming language perspective. Like one is reliability and provability of programs. We haven't talked about this earlier. So we have always, if you recall your software engineering or similar courses, you would remember there are different software development lifecycle steps involving requirement specification, analysis, design, high level, low level, implementation, testing, deployment, maintenance, and so on. But in all these, the correctness of what we have actually created is based on how much we can test. And naturally, it is any complex software deals with potentially infinite domain of computation values, where testing, making an exhaustive testing is impossible, impractical. Even testing all the scenarios that it has been designed for often turns out to be very difficult, particularly for exception situations, because it is very difficult to maybe to simulate that exception situation. So what happens is we have been comfortable living with the fact that software can potentially fail, and after all, it is soft. So if it fails, I'll go back and kind of reproduce that bug, then localize, fix that bug, test again, and we would be happy to go forward. Which is fine in simple applications, which becomes of concern with applications that involve higher risks like online e-commerce and all that. You certainly do not want a software bug to eat up your money or deliver your goods to someone else. But these still are manageable risks. But when software starts getting severely used, as it does today, in mission critical applications like aviation, there's a Boeing, Airbus, the two leading aircraft manufacturers now use about 60 to 70% of the components which are software. I mean, they are basically programs embedded in different control monitoring systems of the aircraft. So the reliability of those software becomes a big concern. I mean, you would not be happy to take a flight from, say, Delhi to Bangalore, knowing that the 70% component, which is software, has been tested at 95% level. And there's a 5% probability that some of this software could fail and lead to a ripple effect of other components failing and, the eventual. So there has been contrary, besides various advances in testing, automation on that, on in terms of finding out repeatability in how to reproduce tests and so on. In addition to all that, there has been a lot of research in what is known as software verification. So what you say is, well, a software, can I prove mathematically that the code that I have written is correct? So if I can prove that, then certainly there is no question of having a test or having, a proof will work for the potentially infinite possible set of values on which the software is designed or the program is written for. So for years, the someone has unmuted. Kindly mute, please. So software verification has become a big area, and there has been significant interest in using languages which are more verifiable than others. So even when code is written in these embedded systems using, say, a language like C, it is not the C that we know. It is some kind of a subset, restricted set of C with some bit of additions, which is pretty much like C, but is different because it is much easier to, or relatively easier, I should say, to test and prove correctness for programs written in that language. Now, in that context, functional programming, though, as we talked in the early part of this course, that when programming started, it was two primary languages, Fortran and Lisp. So procedural and functional started almost at the same time. And then procedural took over, transforming itself with object orientation and so on, because of the volume of common applications that are needed in life. And it progressed, and kind of functional took a little bit of backseat, remaining only in the academia and the research, or remaining confined to variants of Lisp and so on, till the time when people started realizing that if a language is based on a formal foundation like Lambda calculus, which is automatically provable, which where deductions are possible for getting a unique semantics, which is, getting the right semantics is a main problem of, saying whether a program is correct or not. So where these things are possible, certainly it is, beyond efficiency of that implementation, it is of primary importance that you use these kind of programming languages in mission critical applications like aviation, like space science, and so on. So that is the reason, one of the, certainly different style of programming is certainly of interest, but this is one of the reasons why functional programming has been also gaining a lot of ground. So what we are trying to do here is give you the background on the Lambda calculus, the uh, formalism that could capture semantics and type inferencing for all programming languages, and showing that if you if you just remain in the domain of almost pure lambda calculus and based your language like Haskell does, then you will be able to eventually build systems, build programs which are more easily provable in a formal way, so that you have a unique semantics that only is possible through those systems. And on the other side, we are taking a look into the impact of lambdas in common programming languages like C++, showing that now lambdas are making entry into C++ because C++ does have the advantage of being extremely efficient. So if we could have the power of formalism of lambda, provability of lambda brought into C++ in a significant way, then it becomes easier to write more compact code, more provable code, more small code in C++ as well. So these are the two streams we are trying to mix around, and then also trying to see how this principle of lambda calculus and its consequences help in the common compilation tasks of your programming languages, which is type management, type inferencing, and so on. So that's kind of, I mean, just to give you the perspective of why we have been doing, starting with lambda syntax, then we did a lambda semantics, which is still pretty abstract. We will now go into lambda type. We'll go into inferencing based on those types and so on. Along with these streams, how does these languages fit in? And where is the actual engineering requirement, engineering utility of this is what I just tried to give you a glimpse of. So besides these languages, which are purely functional, but I mean, you have already seen the discussion that Srijuni excellently drove, that even between them, there are different variances in terms of, what language gives what kind of flexibility, what is the focus, and so on. And we will also see the use of lambda in our very well-known C++ language. So we will try to kind of keep a balance between the theoretical foundation for the principles and the engineering applications in through which the languages are evolving today. Right. So that's kind of the background to certainly bring in these three languages in the context of our discussions. Now, before I start on to the next module, I would also like to make the announcement that please note that your first class test will be held on 27th January, that is next Wednesday, right? So please be prepared for that. The syllabus for that class test, or the coverage for that class test, will be in terms of module 2, which is lambda syntax, module 3, which is lambda semantics, as we have done so far. That is up to the order of evaluation, normal and applicative order. And this module 9, which is programming in these three languages. The module 4 on typed lambda calculus, which we'll start discussing today and continue on the Monday, will not be part of the class test syllabus, right? So please keep that in mind. There will be formal mails sent out by the TAs as well. And the test will be held during the class hour on Wednesday. Exact start time, we may keep it little later than 8 o'clock because I've seen that you get some of you get delayed to report to the class. So we will start. We'll give a start time, and the duration will be for 1 hour. It will be an online test on Moodle, where you will all those links, test links, and so on will be given. So when you'll have to log in, and when the test time starts, the questions will become open to you. They will come to you in certain order, and the order may be different between what you see and what your friend sees. And you'll be able to finish one question and only then answer that, and only then you'll have to go to the next question, and you cannot come back to a question which you have already answered. So in this way, it will be a 1 hour test. Uh, there is some questions coming up, I can see. Yes, yes, of course, Shomnath. It will be done today itself, right after this class. So for module 3, the module will be uploaded. For module 9, it will be some of slides and then the worksheets that Srijani has shown. So for module 9, it will be more required that you go through those worksheets, install these languages on your system, language interpreters on your system, and practice them. Right? So this is this was the important thing that I wanted to tell you. Of course, mail will go out, but it is critical that you start getting prepared for your class test as well. Yes, some. It is. Yes, it is. It is auto-evaluated test. Let me put it this way, Nagesh. So question types typically, obviously, is significantly objective. So there'll be multiple choice questions. There'll be multiple select questions where one, zero, one, or more than one answer may be correct. And there could be short answer type question where it's kind of you are given a problem, you have to fill in the answer where the patterns will be matched between what you write and what is the correct answer. And you will be told how to write that. It could be matching of items into lists, this kind of. But long handwritten questions will not be there because this is an online automated test with auto evaluation, right? So I hope that answers you, Nagesh. Right? Okay. So yes, good, good. So I think there is no further question on this logistics. And obviously mail will go out and the contents will get uploaded immediately. Okay, so let me go to then start on the next module. Just 1 second. I hope you can see this, see the presentation, right? Okay, so far we have seen the syntax of lambda expressions and the semantics of it, which is basically normal form reduction of a lambda expression. Now what we bring in is what is called a typed lambda expression. That is, if we the different components that we have, what if we have types associated with them, and how does type really make the semantics and the correctness of the expressions meaningful? So we will now bring in the concept of type and type expressions, and then see how types can be put on lambda expressions and how that can be checked in an automated manner. So what we start with is what is called simply typed lambda calculus, which does not assume any other operator than what you have already built the lambda calculus with. So we'll come to that. So initially we start with an arbitrary collection of type constants, typically written as TC, which may include constants like integer, boolean, etc. So which you say are known to you a priori. These are types which are known to you. Then the type, a type of an expression in simply typed lambda calculus is, as you can see, that simply typed lambda calculus is written with a capital lambda with a superscript of right arrow. That's the notation. So if T is a type, then either T is one of these type constants. That is, C belongs to TC. So it could be integer, it could be boolean, like that. Or it is a mapping from type 1 to type 2. So it's a mapping of one type into another. So you can easily see this is a function. Or it could be parenthesizing, which is purely syntactic of a given type expression, right? So this is primarily to take care of the precedence, as you can understand. Now, obviously, when we put this type expression, see the type constants come from TC. So this expression is in the context of the collection of type constants, but we will not always keep on writing TC along with this, meaning that, well, there's a TC and we know that. We go with that assumption. So these are the three, as we have seen, of a constant or a mapping or a parenthesizing. So typical elements of type could be integer, boolean, it could be integer to integer using this second rule. It could be boolean to integer to integer. So it is integer to integer, then you parenthesize, you get another type. You use that type as T2 here, you get a type, and so on. So these are the different, these are called type expressions. These are not value expressions, because here everything is a type, right? So we'll have to associate the types with this. So when we define the expressions of a typed programming language or typed lambda calculus, we distinguish between what is known as a pre-expression and what is the expression of the language. A pre-expression is one which is syntactically correct. So we have learned the syntax. So according to that syntax, it is a correct expression. Then we say it is a pre-expression. But all pre-expressions may not be typeable. I may not be able to give a well-defined type expression to that. So a pre-expression which is just syntactically correct by being a pre-expression but not typeable will not be called an expression. We call it an expression when it passes through the type checker. So a pre-expression promotes to the expression when it passes through the type checker, and it has a type which is valid, which is unique, and which can be checked for. So just introducing the term, slowly examples will make it clear as to what we are trying to say. Now, the expressions of the type lambda calculus can include elements from an arbitrary set of constant expressions. We allow constant expressions also. We have seen in earlier lambda calculus also. So it may include constants of type integer. So we have assumed type constants. Integer is a type constant. Boolean is a type constant. So along with that, we associate expression constants. These expression constants we earlier also had when we defined the lambda expressions originally. So type constant integer has expression constant 0, 1, 2, like that, just to indicate that they are different from 0, 1, 2 that we use. They are expression constants of the language. We are putting underscore, just a notational convenience. Similarly, Booleans have two expression constants, true and false. And we have operations in that, like plus, mult. So for example, if I say a plus operation, then it will have a type expression which is integer to integer to integer, because it takes two integers and produces an integer. So this is just a carrying form of notation, that plus takes an integer and produces a function which is integer to integer. So this is the type expression that will be. Now, usually what we'll do, we will not try to enumerate this set of constant expressions EC. We'll usually keep it unspecified, and using the symbols wherever it can enhance our example, because EC, the elements of EC were the elements of different type constants will be the common types that we deal with, but constant expressions will be important. So given this, the collection of pre-expressions of the type lambda calculus, it is called type lambda calculus expression, are given with respect to these three things. One is we have a collection of type constants, because those are the constants in terms of which we want to express type. We have a collection of expression constants we have just introduced, EC, and we need variables in the lambda calculus we have seen, lambda expression we have seen. So we have a collection of expression identifiers. So earlier we were just using variables, whatever comes to our mind. And now we are saying, okay, whatever variables, you choose the variables in the same way, but let's say EI is a set of all those variables or expression identifiers that I have. So then, using the definition of lambda expression, we can define a typed lambda calculus expression like this. If M and N are two typed lambda calculus expression, then a typed lambda calculus expression is either a constant, which is an expression constant, which like 0, 1, 2, true, false, like this, plus, minus, all that. So it could be an expression constant. It could be an expression identifier, a variable. Think about the basic, building rules of lambda calculus. It could be a variable or expression identifier coming from EI, or it could be an abstraction. Abstraction so far was written as lambda x dot m or lambda x dot e, which is x is the binder and this is the body of the abstraction. But now we are qualifying x with a type t. We say x is of type t, which is a type that we associate with this binding and to be used in the expression m, which is the body of this binding. So this is how the abstraction changes. Mn is the application. Both are typed lambda calculus expressions, so it applies to n. So these four come trivially, or not trivially, I should say quite in a direct manner from the syntactic definition of lambda calculus. We add one syntactic sugar by letting parenthesized expression to be a part of the typed lambda calculus expression. So if m is a typed lambda calculus expression, so is parenthesized m. Now, naturally, you can see that this whole set of typed lambda calculus expression will be parameterized by TC, of which every T will be a member of, by EI, parameterized by EI, of which every expression identifier X would be a member of, and EC or expression constant, of which every C would be or constant would be a member of. Right? But we will not explicitly write that. We'll assume that these three are known to us or can be made known to us. Right? So these pre-expressions are we are still calling them pre-expressions because we'll be able to call them expression only when we have done a type checking for each one of them. So this is basically explanation of what I have just said, written down for your future reference. So in order to complete the specification of the expression of the type lambda calculus, we need to write down the type checking rules. That how do we check the types? So that we can apply it to a pre-expression and see if it is type correct. So far, pre-expressions are syntax correct. So we need to see if it is type correct, and the expression being checked often include identifiers, typically as formal parameters along with their types. And in order to check the type expression, we need to know the type of each identifier. So that's a basic task. So that we can graduate to having expressions which are collection of expressions of the type lambda calculus with respect to the type constant and expression constant, which are pre-expressions which can be assigned a type by the type checking rule. And the interesting thing is we'd like to make the type checking rule automatable, obviously. Now there is a question that comes up. The question is again back to free and bound variables, right? So we all now know as to what is a free variable, what is bound variable. I'll very soon explain as to what is their context in type checking. But let us just go through the quick notation. Let's say if I have an expression M of type lambda calculus, then we say the collection of free identifiers of M are written as FIM. Earlier we used some notation FV like that. So here we say it's a FIM, free identifiers of M. How do you define it recursively? If M is a constant, naturally there is no free identifier, so the set is null. If E belongs to EC, expression constant. What if M is a identifier itself, X belongs to EI, so free, this X is free, so the free identifier of M is a set containing X. What if I try to compute it for an abstraction where X is of type T and M is the expression? Obviously, whatever is free in M might include X. So X has been bound here. There's a binder on X by lambda X. So I will compute the free identifiers of M and take out X from that. Subtract the set containing X from that. That is the free identifiers of M. For an application, free identifiers of Mn, this application is free identifier of M union free identifier of M. Right. So anything, an identifier used as a formal parameter of a function, then its occurrence in the function body is no longer free. We know that very well. We say those are bound identifiers. So these are again repeat of examples that you have seen several times. So if you have if you compute free identifier for plus X, Y, then you get X and Y because none of them are bound. If you compute it for free identifier for lambda X colon integer dot plus XY, then X is obviously bound by this binder. So Y is only free. So you can see that very easily. Now the question is, why do we want to really differentiate between free and bound identifiers? The reason is simple. If you go back to the definition of type lambda calculus, you can see that here, when I'm making an abstraction, the binding variable X, right, the X that is being bound here, or in simple terms, the parameter, is being given a type. That is the requirement of the type calculus. That I must know the type of the parameter. So when I want to find the type of M, for all occurrences of X, I will know its type. But if M has some variable which is not bound, then the type of that variable does not come through the parameter. So if I have a free variable in M, the type of that is not specified within this abstraction. So it will have to be externally specified. So very simply talking in terms of a C program, if I have a parameter, I know its type. So within the body of the C program, I know what is the type. If I have a local variable, I know its type. So I can look at the function and talk about the type of parameters and local variables. But suppose I have within that function used a global variable. Naturally, it is declared outside of this function earlier. So from the function abstraction, which is this is a function abstraction, that is C function and its body. From that, I cannot know what is the type of that global variable, static variable. I have to know it externally, right? So that is the reason that you need to separate out the free identifiers through this algorithm, because the free identifiers will not get their type through the parameter mechanism. So the type checking rules will require information about the type of the free identifier. So what we say that we handle this problem by saying that, we build up something similar to the global space in C, C++. We say that there is a static type environment, that whenever we are assigning or trying to do type checking for a pre-expression, there is an environment E which associates type with free expression identifiers. So E will associate, it is a type environment, static type environment, static because it does not change with the expression. It is a finite set of associations between identifiers and type expressions of the form x colon t, where each x is unique in t, e, and t is a type. Naturally, you can understand that I cannot have two functions referring to two global variables of the same name and having different types, right? So every identifier in the static type environment has to be unique, and it will have a type which is set in this environment. So your type checking will not be just independently checking for that expression, type of the expression, but it will also be in the context of this static type environment. So if x colon t, that is x of type t, belongs to the environment, then we will sometimes write it in a different notation. We'll say that the environment value of x is t. This is just a notational convenience. So now we will have type checking rules written in this form. We will say that in the context of the static type environment E, expression M has type T. In the context of, because if anything is free, then in E it has some type which can be different for different environments. So it is always in the context of E. Or we can write it like this, kind of a fraction notation where there is nothing on the top, difficult to understand. We'll come to the second form of the rule. So this is kind of a type checking rule, very typically written, where the top of the rule is the antecedent and the denominator of the rule is the consequence. That is, it says that, just read this, E implies M1 is of type T1. That is, given the static environment E, M1 has a type T1, M2 has a type T2, and so on, Mn has a type Tn. If this is true, then M has a type T. Right. So these are kind of said to be rules or assertions where the type of M being T is dependent in the type of M1 being T1, M2 being. So this is what is called a rule. So a rule is a if this, then this, right? So antecedent and consequence. Here it is written in the assertion form with a kind of a horizontal bar, right? The hypothesis of a rule all occur above the horizontal. This is a hypothesis precondition, and the conclusion or the post condition is below the line, right? This is the form. So now let us look at what are the rules. So we have, again, allow me to go back once more to remind you. So this is your typed lambda calculus expression. So there are 5 different ways to build up the expression. Okay? So what we'll have? We'll have for every such expression, every such builder of expression, we'll have a type checking rule so that it can be easily made a complete set of rules. Come back. So for identifier, what you have is whatever is the environment, you add the type of that expression identifier to that environment. So there's no precondition because obviously it has to be unique, so it's not there, or if it is there, it has to have the same type. So we don't need a precondition. So we say that whatever environment exists, I add the type of this variable, which is t, to the environment. So given that E union X colon T, the consequence is X is of type T, which is kind of saying the trivial. Right? For a constant, we know the type. What is the type? Type is the what comes from the type constant, the pre-assigned type. So if C is a constant expression, then given the environment, we know what is the type of C. Now comes the parent function. So, which is abstraction basically. So what we are saying here is the type of the parameter is T, X is T. So I have an environment and a parameter which is of type T. Right? So in that context, if the type of M, the body is T primed, then this is a function from T to T primed. What is a function? Function is a mapping from one type to another type. Add is a function which takes two integers, gives me one integer. So the type of parameter of add is a pair of integers. So it is int cross int. T is int cross int. And what should it return? What is the type of the body is what it returns, which is int. So T primed is int. So we conclude that the type of add function abstraction is int cross int maps to int. Right? So this is the simple function rule that given the type of the parameter in the context of static environment, if the type of the body is T primed, then the function has a type which is T to T primed. Next, the second important rule is application. So we want to see what is the type of M applied to N. Now, if M has to apply to N, M has to be a function. So in the environment, in the context of the environment, M must have a type which is T to T primed. If it is not, this rule is not applicable. You can easily see now that you can get expressions which are correct, but will not be type correct. Right? I said 2 applies to 3 is not type correct. Because 2 is not a function, it cannot be applied onto 3. But it's a correct lambda expression. So if M is an abstraction which maps from T to T primed, and also if the static environment implies that N is of type T, which is the actual argument on which M applies. So M maps from T to T primed. It takes a parameter which is of type T. So what is the result of applying M onto N is T primed. So if I take that add function which is int cross int to int, and I take a pair of integers 2 and 3 and apply add onto that pair, I get 5, which is of type int. So if the function has a type T to T primed in the environment and the argument on which it applies N has a type T, then M applied to N has a type T primed. Now, naturally, this says a lot of things. It says, for example, if M is not a mapping type, then this rule, the hypothesis of the rule is not valid, so the rule will not apply. Type will not get checked. If the type of T here and the type of N, this T here are not same, that the function maps from bool to int, and I pass it a parameter which is string, then the type cannot be checked. This type checking will fail. So they will have to be the same. But if it is, then the consequence is that M applied to N has a type T primed. Finally, the parenthesis rule is trivial in the context of the environment M. In the context of the environment E, if M has a type T, then parenthesized M has a type T. That is, parenthesizing has no effect on the type. Right? Let me stop quickly here before getting into examples to see if in principle you are understanding the idea of typed expressions. Any questions, anybody? No. Okay. So let us take examples. I think that is what you may be still groping in the dark. So these 5 rules to remember: identifier, constant, function, application, and parenthesis. All are, I mean, once you know the form to write, they are kind of trivial. So let us go to an example. So the typical way is to read the rule from bottom left in a counterclockwise direction in this, and you, if this is a precondition, then this is what the consequence will be. I have just written down what I explained so far. So identifier rule, constant rule, the function rule, the application rule, and the parent rule. All, each one I have given a small explanation for your future reference. Now let's determine the type of this expression. So where we assume that integer is a type constant belonging to TC, plus is a constant belonging to EC, and plus has this type integer to integer to integer, and the static environment to start with is empty, has nothing. Right? We are starting with a clean slate. Right? So the question to answer is this: given E naught, which is the empty static type environment, what is the type of this expression? Right. So we can see that there is a function here. Right. So we have to type check this function. So for that, we must check the type of the body, which is plus x x. This is a body. So we need to know the type of that body to be able to check for the type of this whole expression. Right? So what we have got x is of type integer. So we put that in the static environment. We say E1 is E naught union x colon integer. Naturally, E naught was 5, so it is x colon. E1 becomes x colon integer. So now we have to see that in the context of x colon integer, what is the type of plus x x, right? Because this is what we have so far. Now we have to check. I mean, this is just explanation of what I said. Why this gets into the environment is by naturally the identifier rule, because this is defined to be of type integer, so it gets into the environment. Now to check plus x, we say that we will apply the constant rule, because plus is an expression constant. So we know the type of plus is this integer to integer to integer. So we will put it to the environment. So E1 also has plus having type integer to integer to integer, and x having type integer. So first is by the constant rule and the second is by the identifier rule. So if I have, so now I have plus x, that is the first application plus x. So I look at the application rule. So plus x, so m is plus, n is x. Now what is the type of m? Is integer to integer to integer, t to t primed. And what is the type of n, which is x of integer? So if I apply t to m to n, we get t primed. So we'll be able to say that applying this, I get plus applied onto x has a type integer to integer. Okay. Very simple application of the use of the application rule to get the type of plus x from the type of plus and the type of x by using this rule. If it is integer to integer, then I can again use the next application, which is plus x applied onto x. So plus x has a type integer to integer. We have got here x as a type integer. So t is integer to integer. And this is, I'm sorry, t maps to t primed is integer to integer, which is m. N is of type integer. So t primed is integer. So this application will give me an integer. Okay. So this is. So now what I have the type for plus x, x, which is integer, which is t primed, m here, t primed. X is of type integer, we already have in the environment using the identifier rule. So t is integer. So the type of this abstraction is integer to integer. So I can say that lambda x colon integer dot plus x x is integer to integer, right? Which matches the intuitive notion of this type, which is plus x x is adds x to itself. So given an x, which is an integer, it will obviously give me double of that, which is also an integer. So that's the, I mean, that's the operational semantics that we are familiar with, but here we are getting to those by using these type checking rules in a formal manner. Okay. Now, typically, these are written in a what is known as a ladder diagram. So we are coming from, this is top of the ladder is the beginning of the deduction. I'm sorry. So I have x of type integer, identifier rule. I have plus is of type integer to integer to integer. I'm just writing int here because I was running out of space in the width of the slide. Otherwise, there is no different meaning of this int. It is same as integer earlier. So this is what I get. So these two I get independently. So they are at the same level. So this is by the constant rule. Now I combine these two in the antecedent of a function application rule. The third is function application plus x. Plus is being applied onto x, function application rule. And I get int to int. I got int here, I got int here, they matches. So I'm left with int to int. So this is the third in the ladder. For the fourth one, I again need x to be of int because I want to apply plus x to x. So again, I use the first identifier rule at the same level here, where I have plus x as int to int. I have x of type int. So plus x x is an application here, int, int. So its type is int at the next level. 4 application has happened. Now I need to have the function, which is an abstraction on this. So I have x of type int, I have plus x, x of type int. So I have actually here I should again I should have again written this E1 has x of type int because you have this binding. And I get this result. It is very typical of writing it in terms of a ladder diagram so that you can really see how the deduction system is advancing. And the important thing to see here is not only the fact that you are able to deduce the type of this whole expression. So it becomes a typed lambda calculus expression. But the important thing to see is every step is mechanical in nature. I mean, we are not using any separate human intelligence to get to this type deduction. So this whole thing is is a formal way which can be done in an automated manner. So now say if we extend this to say determine the type of lambda x colon integer dot plus xx applied onto 17, where plus is this, then we can use the earlier result that this lambda expression, this lambda abstraction is integer to integer. By constant rule, 17 is an integer. So again, by application rule, this is integer to integer, this is integer. So what I get is an integer. So I can say that this whole expression is actually an integer. So just building it up further. You can determine the type of lambda x colon integer, x plus 40 applied onto 2. Just shown here for, this is just kind of to get you familiar with this. So E naught is empty. So initially what you have is plus, which this is the first that will have to get applied. So plus into int, and then I have x, which is int. So I will have plus x, which is into int. By constant rule, 40 is int. So I have an application of plus x on 40, which int matches, which gives me int. Then I have an abstraction on this, which is x int plus x 40, which will get me end to int. I should have again written here x is int. Then independently I have 2 is int. So I have an application of int to int. 2 is int. So I get finally that this whole expression has a type which is int. And that's how the ladder diagram help us to get to the type checking. So there is another here which you can certainly work out. There's another given here which is also worked out. There's another given here, another given here, and a whole lot of practice problems are given for your practice. The solutions are given herein. I would suggest that you don't jump onto the solution. First, try it yourself, and that will give you a good amount of practice. So that brings us to the end of simply typed lambda calculus. Let me see if there is any question. So in this we have tried to define type expressions using a set of type constants and expression constants and expression identifiers. And now we are trying to associate type with an lambda expression, which we are now calling as pre-expression. So if we can associate a type with it, we say it will be an expression. And for that, we have defined 5 specific type checking rules. So given any expression, we will apply these rules and we will try to deduce the type. If it can be deduced, then it is a typed expression, an expression. Otherwise, it remains just a syntactically correct pre-expression. And the additional factor that we have looked into is that it has the bound variables get their type through the provided parameter type. The free variables will have to be given a type from the environment. So for that, we are making the context of a static environment wherein all free variables will be associated with certain type, and based on that, the type checking will apply. So this is all that simply typed lambda calculus that we have been able to do. Any questions? I think today's class has been heavy with 3 languages and 1 typed concept. Anyway, there is no question, so let us stop here. On Monday, we will continue with the extended type lambda calculus. That is necessarily what we'll do is, so far it is nice to see everything in terms of function and function application, but that's not very pragmatic in terms of programming languages. The programming languages do have tuples, they have structures, they have arrays, and so on. So we would see that what happens if we use the notion of the basic lambda calculus and extend for these operators. How does the expressions extend and how does the corresponding types extend? So that is the part of extended typed lambda calculus, which we'll discuss on Monday. And again, a reminder for your class test on the next Wednesday, covering module 2, 3, and 9. Okay, then, if there is no further question, let me stop here today. Thank you, Srijan, for your presentation. There is some question coming in. Is a deadline of assignments on consecutive days? Can it be extended? What is the deadline, Srijani? Srijani, are you there? Or Shoman? 21st and 22nd. Okay, we'll extend it by 1-2 days. That's fine. We'll do that. But it is important to complete both of them well before your class test, because these assignments are based on your class test syllabus, right? They are based on module 2 and module 3. So unless we have a closure for these assignments, we cannot announce the solutions, which will be important for many of you to know, so that you can prepare for your class test better. So, Srijani, Shoman, please try to extend these deadlines by, say, 2 days. That should be fine, right, Tanu?
Okay, sir.
Okay. That's okay. That's fine. So still it will be over by 25th when you get to know the correct solutions, and you can still have 2 days to prepare. And we will not have separate assignment on module 9 before the, I mean, we will not have a separate assignment on this, but it will just be asked in the class test. So prepare on the programming languages on your own. Okay. Thank you then very much for this early morning attention. We will now close. Have a nice day, and we will meet on Monday next.